Hello everyone, and welcome to this talk about an improved approximation algorithm for the asymmetric trailing salesman problem. So what I present today is some joint work together with Jens Pigen. So let's start. What is the asymmetric trailing salesman problem? So an instance of ATSP consists of a directed graph G with vertices and edges, and then for the edge, we are given a non-negative cost. And the task is to find a walk in G that visits every vertex at least once, returns to its starting point, and is of course as cheap as possible. So what do we know about this problem? Let me start with a brief overview of the history. So the first non-trivial approximation algorithm is from the 1980s, which is the classical cycle cover algorithm, which gives a log to n approximation ratio. And then there has been a sequence of results that improve the constant factor in front of the log n. So this already shows that it was kind of hard to improve over these order of log n approximation ratios. But in 2010, there was the first big important breakthrough, where ATSP gave an order of log n over log n approximation algorithm. And in 2015, Ola Svensson gave a constant factor approximation algorithm for a special case, namely for the so-called node-weighted instances. And then finally, 2 years ago, Svensson, Tarnowski, and Weg gave the first constant factor approximation algorithm for ATSP. So they first proved an approximation ratio of roughly 5,000, and then they later optimized the constant and achieved an approximation ratio of 506. And the result I want to talk about today is that we could improve this approximation ratio from 506 to 22 plus epsilon for any positive epsilon. So all these approximation algorithms compared themselves to the optimum value of the standard linear programming relaxation, and that's the following. So we have a variable for every xe for every edge e in our graph, and then of course we minimize the total cost. And as constraints, the first type of constraints says that for every vertex, the number of incoming edges should equal the number of outgoing edges. And then the second type of constraints is that if you look at a subset U of the vertices, then the total number of edges entering the set U and leaving the set U should be at least 2, because of course we need to enter each of these subsets U at least once and leave it once. So in total we cross the boundary at least twice. And then we have non-negativity constraints. So the quality of the linear programming relaxation is basically, so the quality of the lower bound we get from this is described by the integrality ratio. So the integrality ratio is the maximum ratio between the cost of an optimum solution compared to the cost of an optimum LP solution. And we know that the integrality ratio is at least 2, so that's the best lower bound we know. And the best upper bound, due to Svensson, Tarnowski, and Weg, is that the integrality ratio is at most 319. Now the main result of our work is that for every epsilon, for every positive epsilon, there's a polynomial time algorithm that computes for every instance of ATSP a solution of cost at most 22 plus epsilon times the cost of an optimal LP solution. And this has two implications. So the first thing is there is a 22 plus epsilon approximation algorithm for ATSP. And the second consequence is that the integrality ratio of the LP is at most 22. So in the rest of the talk, I will want to explain you some of the ideas that we use to prove this theorem. And so algorithm for ATSP heavily relies on the work by Svensson, Tarnowski, and Weg. And the way they gave their constant factor approximation algorithm is they started by ATSP and then they applied a whole sequence of reductions, reducing the problem to more and more structured instances until they finally ended up with instances on which they could give a constant factor approximation algorithm. And now for comparison, our algorithm also uses a sequence of reductions. Yeah, so the reduction steps are somewhat similar, but there are several small differences. And there's like the most important difference is that we could skip completely this one step, which is called like irreducible instances in Svensson, Tarnowski, and Weg's algorithm. So we don't need this one reduction step and we can skip this completely. So overall, we in fact we don't only get a better approximation algorithm, but the whole algorithm also becomes simpler. So in our algorithm, we use, of course, very many concepts of Svensson and Tarnowski and Weg, but we also improve on each of their reduction steps. So in the first step, we prove some stronger properties that lead to a simplification of the overall algorithm. So this doesn't help with improving the approximation guarantee, but it simplifies the arguments. In the second step, that's where we make the most important changes. We give a much simpler reduction to vertebrate pairs, skipping the step of irreducible instances, and that's where we simplify the algorithm most and where we also gain most in the approximation ratio. But we also give a better algorithm for vertebrate pairs, and our changes in this step allow us to achieve an approximation ratio that matches the upper bound on the integrality ratio up to an epsilon. So before Svensson, Tarnowski, and Weg could show that there always exists an optimal solution to ATSP, or there always exists a solution to ATSP that costs at most roughly 300 times the LP value. But if they want to compute a solution in polynomial time, they could only get one which costs roughly like 500 times the LP value. So there was a discrepancy between the best upper bound on the integrality ratio and the best approximation ratio that we can achieve in polynomial time. And our changes in this last step allow us to close this gap. So in the following, I will show you some of the ideas in more detail. So I will explain some of these steps in more detail. I will mostly focus on the second step because that's where we make the most important changes. But let's start with step one. And step one is about obtaining structured cost functions. And let me not go into details of exactly how the reduction works, but let me explain you what we achieve in this step one. So the result of step one is that we show that it suffices to consider a so-called strongly laminar instance. So what is this? In a strongly laminar instance, we are given a laminar family of vertex sets. So a laminar family, as you can see here in the right in the picture in the right. So in this laminar family, if you look at any two sets in the family, either the two sets are disjoint or one is contained in the other. And then we are also given a non-negative or a positive value yu for each set in our laminar family. And this laminar family defines, together with these y values, now defines our cost function. Namely, if you look at a set E, so like one shown in this picture here on the right, and then we always pay the value yu whenever we leave or enter the set U. So here in the picture, you see for this black edge E, you see these sets marked in red, and the cost of this edge E is simply given by the sum of the yu values for these red sets. So so our cost function has this very simple structure. We have this laminar family, and we pay whenever we leave or enter one of these sets in our laminar family. So this is a property that already Svensson, Tarnowski, and Weg achieved. And what we added here in this step is the second property. Namely, we show that we can assume in addition that each of the subgraphs that are induced by one of the sets in our laminar family, that all these subgraphs are strongly connected. So why is this useful? So intuitively, the reason is the following. Let's say we want to go from one point A inside a set U to a different point B inside a set U. Then the second property is strong connectivity tells us when we want to get from A to B, we don't have to leave the set U and then re-enter it again. And that's a good thing because for leaving and entering the set U, we pay because that's the structure of our cost function. So this is the intuitive reason why the second property is useful. And so this, what I gave you here in the slide is sort of the result of step one. So in the following, we can assume that our cost function is given by such a laminar family, L. So now let's get to the second step of the algorithm, and that's going to be the main part of this talk, reducing to vertebrate pairs. And we'll come to the definition of vertebrate pairs, what this is. I'll explain this in a few minutes. So what's the basic idea of the second reduction step? So far, I've showed you what the strongly laminar instance of ATSP is, and In fact, we can show that we can reduce to this. And now we want to solve these, want to find a good algorithm to solve strongly laminar instances of ATSP. And this strongly laminar instance of ATSP, our cost function is given by this laminar family that I explained to you before. And I suppose each of the sets in our laminar family would consist only of a single vertex. So all our sets in the laminar family are singletons. If that was the case, then we would have an instance which is a node-weighted instance of ATSP. And for this, Svensson already gave a constant factor approximation algorithm. So what we would like to do is we would like to reduce strongly laminar ATSP to node-weighted ATSP. And so this is what we'll try next. So I will give you a naive algorithm how we could get from strongly laminar ATSP instances to node-weighted instances. This naive recursive algorithm will not be good enough, so we'll later show you how to fix it, but it gives you kind of the basic idea of the algorithm that we use here. So we start with our strongly laminar ATSP instance that we would like to solve and would like to reduce to the case where we have only singletons in our laminar family. So now we don't have, of course our laminar family contains also other sets that are non-singletons. So what we simply do is we look at the maximal sets in our laminar family. These are the blue ones here, and we contract them. Then all our sets in our laminar family are singletons only, of course, after the contraction. Then we can apply Svensson's algorithm for node-weighted ATSP. We obtain a truer, but of course then we need to uncontract the whole thing. Now it can happen that we enter one of our blue sets at one point and leave it at different points, so we need to add some short orange paths here to connect things again. Now our subtour here, so the tour that we get here visits each of our dark blue sets here, but it doesn't visit every single vertex. So inside each of these blue sets, things might be disconnected, and that's why we call our algorithm recursively inside each of our blue sets. So this algorithm will output you some feasible solution for ATSP. The question is, of course, how good is this tour? And to analyze the algorithm, we use the concept of nice path, and so we call that it might have happened that we leave and enter one of our blue sets at different points, and we had to add these orange paths here. And now the question is, how expensive can these paths be? And we call that we pay whenever we leave or re-enter one of the sets in our laminar family. So what we can show is that we can choose these orange paths to be always what we call a nice path. And what is a nice path? So a nice path is a path that never leaves and re-enters the same set in our laminar family. So it is okay to enter a set and then later leave it, but it's not okay to leave the set and then re-enter it. And intuitively, nice path always exists, because suppose our orange path would leave and then re-enter the same set in our laminar family, then we could also shortcut inside, because the subgraph induced by this set L in our laminar family is strongly connected. That was the property that we proved in the first step. So this was one of the properties of our strongly laminar ATSP instances. So having these nice paths allows us to bound the cost of our algorithm on a single level of our recursion. And on the single level of our recursion, using these nice paths, we can make sure that we won't cross the boundary of the sets of our laminar family too often. The issue is, if we apply the recursive algorithm, it could be that there are many and maybe also expensive sets in our laminar family that we basically visit on every single on every single recursion step. So we might call the algorithm like many times recursively, and every time we pay for leaving and entering this one set in our laminar family. And because of these recursive application of the algorithm, it might happen that the set in our laminar family contributes to the cost of potentially all order of n many recursion levels. And that's why this simple, naive, recursive algorithm has an approximation ratio of order of n only, and it's not a constant factor approximation algorithm. So we need to do something more clever. We need to be a little bit more careful, and that's why we use vertebrate pairs. And using vertebrate pairs, we can fix this approach using this recursive algorithm. So what we tried so far was reducing stronger laminar ATSP to node-weighted ATSP, because for this, we already have a constant factor approximation algorithm. This didn't quite work, so this was maybe too much to hope for. So what we do instead is we reduce the strongly laminar ATSP to vertebrate pairs, and then we need a third step, namely we need to adapt Svensson's algorithm for node-weighted ATSP to vertebrate pairs. So now let me explain you what are vertebrate pairs. So vertebrate pair consists of a strongly laminar ATSP instance, so an instance of ATSP, together with our laminar family that defines our edge cost. And moreover, we also have a backbone B. And the backbone, that's what you can see in blue in the picture, is a subtour, so a tour that visits some but not necessarily all vertices, which has the additional property that it visits every non-singleton element of our laminar family L. So in the picture, these non-singleton elements of the laminar family L are shown in green, and our backbone visits all of them. Now the task is, in a vertebrate pair, is to complete this backbone B to a tour. And so now we want to reduce to vertebrate pairs. So in the following, we'll assume that we already have a good algorithm for solving vertebrate pairs. So what's going to be the strategy? Well, basically the idea is we try to do the very same thing that we did before. So we try to apply our naive recursive algorithm, but now we don't reduce to node-weighted instances, but to vertebrate pairs. So let's see how this works. So the first step of our algorithm is we compute a subtour. I will come to how we do that precisely. So this is our blue subtour here, and this should become our backbone. However, our subtour is maybe not a backbone yet, because here these two dark blue sets are two non-singleton elements of our laminar family, but they are not visited by our blue subtour here. So what can we do in order to make our blue subtour becoming a backbone? We just do the same thing as before. We simply contract the two dark blue non-singleton sets in our laminar family. Now the blue subtour became a backbone. So now we have a vertebrate pair, and we can apply our algorithm for vertebrate pairs, which we assume to exist. Or we also assume that there's a good algorithm for vertebrate pairs. So now we have a tour in the instance where we contracted these dark blue sets. Now, of course, we have to uncontract, and the same thing as before can happen. It might happen that we enter one of our dark blue sets at one vertex and leave it at a different vertex, so we might need to add these orange paths to reconnect things. And it can also happen that inside our dark blue sets, things are disconnected, so we might need to call our algorithm recursively. So now what's the gain that we get from using vertebrate pairs instead of node-weighted instances? So as you might already guess from this example here, vertebrate pairs allow us to do much less recursion. So we only need to recurse on these non-singleton elements of our laminar family that are not yet visited by the backbone, and not on all the non-singleton elements of our laminar family. Of course, this helps us only if we find a good backbone that visits many non-singleton elements of our laminar family already. So let me show how we compute this subtour, so this light blue subtour here, that becomes our backbone. So let's recall that during our algorithm, might happen that we leave and enter one of our dark blue sets at different vertices. And in this situation, we had to add these orange paths to reconnect things again. And for this, we could choose these nice paths that had the property that they never leave and re-enter the same set in our laminar family again. Now the idea is the following. So now the next step of the algorithm would be to call the algorithm recursively inside the set L. And in this recursive call, we now want to use this nice path, this orange nice path, to construct our backbone. So we simply take this nice path, and then we connect the endpoints of this path in order to obtain a subtour. And so what's the idea behind this choice? So the idea is the following. Either our orange nice path is cheap, that's good, then we gain something, of course, because the orange path is cheap. Or if the orange path is expensive, then the only reason why it can be expensive is that it visited or crossed the boundary of many sets in our laminar family. And if our orange nice path crosses the boundary of many sets in our laminar family, then in our recursive call of the algorithm, so on the right, we'll have a great backbone, because the backbone visits already many sets of our laminar family. So basically what happens is, the more expensive our orange nice path here is, the better is our backbone when we apply the algorithm recursively inside this blue set L. And this is somewhat the key point in the analysis that allows us to prove the following. So in contrast to before, where a single set in our laminar family could contribute to the cost of all order of n many recursive calls of the algorithm, here we can show that in the analysis, a set in our laminar family will contribute to the cost of at most 2 recursion levels, and not order of n many as before. And this is somewhat the key fact why this recursive algorithm now, using vertebrate pairs, gives a constant factor approximation ratio. So now let me close this talk with giving a brief overview of the overall algorithm again. So step 1 was that first step, we obtained these structured cost functions. So these were the strongly laminar ATSP instances. And for this, we used the dual LP and complementary slackness to prove this. And the second step is then using this recursive algorithm to reduce to vertebrate pairs. That's what I was talking was the main part of this talk today. And then the last step that I didn't talk about at all is that we also, of course, need now an algorithm for vertebrate pairs. And for this, we use an enhanced version of Svensson's algorithm for node-weighted ATSP. And this is then combined with some carefully designed circulation problem. And this now leads to the following state-of-the-art for ATSP. So what we get is that the best known upper bound on the integrality ratio for ATSP is 22. For node-weighted ATSP, the best known upper bound is 13. This was proven by Svensson. And the best known lower bound on the integrality ratio is 2, which holds also for node-weighted instances and unweighted, and even for unweighted instances. And in terms of approximation ratio, the best upper bound for ATSP is 22 plus epsilon. That's what I was talking about today. And with the techniques from this paper, we can also show that for node-weighted ATSP, we get an approximation ratio of 13 plus epsilon.